all the things that could be. Um, Wait another 3 minutes. See, so you guys are on break next week, is that right? Yep. Okay. Um, I can stay after class, by the way, if people want to meet with me about particular things, and I will also schedule office hours from now till the end. I will try to do that. I realize I haven't done it. I will do that, and I also, I just realized I didn't post that video, so I'm going to do that immediately. I also have this. This is our like lining. So you guys, we need to meet about going forward with that. Did anybody test anything yet on anything? Yeah, amazing. Let's look at that. Um, cool. And then I think we have an option today. I can just meet with you about things, or we can try to do that in the next after break. And I can spend today talking to you about like math, which I think is what I'm going to do. I think you guys want me to do that, right? All right, let's do it. All right, let's do it. Let me see your thingy first. Okay. Oh, yeah. Look at that. That looks great. I think this is what we'll do. Excellent. Excellent. Amazing. That's perfect. That's good. Ethan knows. Okay. Yes. Yes. Thanks. Look at that. You did. That looks amazing. Look at that. It's beautiful. Have we got to try to blow smoke through it? Yeah.
I would try to blow it.
Oh yeah? It comes out?
It comes out. It's just at the end. So it might be a little bit.
Yeah, I see. It might. How did you blow it afterwards? Like a little fan? Or?
No, it's not.
Okay. Let's try the smoke. I think we won't know until we put it like if we put it in front of the big fan and turn on and like it might suck it out. Yeah, that's what I'm hoping will happen. But it looks beautiful. Amazing. So attractive. Well done. All right. Let's let me get the fan for you guys after class and we can try the smoky thing. Okay. Okay. So I don't know if I'm gonna screw this up, okay? You can call me out on stuff. This is I have to tell you what the reason for this is very not really related to this class. Although it's related, but I don't think you're going to be using this information necessarily right now. I really believe that there is a universe of ways to describe space that we are barely touching in our daily experience. The physical world is so has been described in so many ways. And one of those ways is mathematics, and one other way is computation, and another way is physical model, and another way is the theory and the metaphors that you speak about, right? And I would like to attempt to open up some connections between those different vocabularies for you guys. And I don't know whether I will be able to convey what I wish to say clearly enough, but I expect that you will have it. You'll have the lecture uploaded, and I believe fundamentally in your individual brilliance. Honestly, I do. To an extraordinary degree. And I think whatever I can manage to convey about this kind of thing will eventually be integrated into an ever expanding worldview. And you might decide that you want to go very, very deep into this computational stuff. And in that case, maybe I can start to provide some of the vocabulary for that. So that's sort of what I'm attempting to do. So this, by the way, this is, I'm not going to show this. This is like a video I posted, or I found, it's not mine. It's a very long, it's like an hour and a half. about all of the physical, about different ways of modeling fluids. So that are not only the way that we've talked about, and like comparing them. I think it's very beautiful video. It's a little confusing, but like it has some beautiful kind of attempts to explain why certain things are physically accurate and other things are not physically accurate, and how our simplifications map onto the world. So I think you should be asking yourselves why something is accurate, maybe on a deeper level. You should be asking yourself if something is simulated in a particular way, what's the proof that that works? What's the proof that it is viable? And I have to say, one of the reasons I am not a mathematician is because I ultimately care sometimes very little about the proof. I just want to be able to use it. And I think if you're a mathematically minded person, you want to know whether it's true or not. Can you prove to yourself that it's true, not just does it work? And so that is kind of the fundamental difference between those worldviews. And there are some texts that kind of go into the background proofs about why we can do some of the things that I'm talking about and why we can't do other ones. And I have one of those texts and I'll post it. I have to say I don't understand the proofs super well myself. Like when you're trying to prove whether something is viable is an order of magnitude more difficult than trying to understand whether how it works. But still, that's there if you want it. Okay. Um, okay. So I've talked about this a million times. The difference between Lagrange and Euler. Fine. The gridded world versus the particle world. So this is the idea that if you were looking at the properties of a particular spot, and basically these three properties at every single spot in this grid, the velocity, the temperature, and the pressure. And that, if you're thinking about the velocity, which is the key one, because it's the one that moves everything else, that is a vector field. Okay? So we can represent velocity like this, with a vector at every point in space. A u and v vector at every point in space, and they would be stored at the center points of the grid. Okay, and I've talked about vectors many times. This is a vector, and you can write it in all of these different ways. You can write it vertically, you can write it horizontally, or you can write it, like that. Okay, and vector fields are very beautiful, as I've said before. And then the other kind of quantity is called a scalar, which I've said before as well. But scalar can be visualized like on a number line. It's kind of like a one-dimensional number. And then this is a vector. Okay. And I talked in my geometry classes about the dot product and the cross product. But those are very fundamental things to understand if you want to work in computation at all. They're kind of key things. So I wanted to make another visualization of how they work, how I think of them in practice, because in kind of a daily way. So these are the normal vectors, right? This is in Houdini. I have a little script. So by the way, everything like that I'm showing you, the files are uploaded, or they will be after this class. So you can see how the visualizations are made. Okay, so this is the normals of the surface. And then that is the cross product of all the vectors with another vector. So basically, any input vector you put in, if I open this up, this one you can see is like I put in a vector, I think that was 1, 1. So it's like on a 45-degree angle. And then all the vectors that used to point out now spin perpendicularly around that 45-degree axis. So if I go into Houdini and I open this up and I go in here and I change the normal vector in here, I change the vector here, they will spin differently around the form. So it's like two vectors always define a plane, and the cross product is the other one that's perpendicular to it. So if you ever want to find the perpendicular frame in a situation, this is how you do it. So I just reviewing these concepts, but with a visualization, because I feel like we don't talk about them in their practical way quite enough. Okay. And then this is just a demonstration of the dot product. Okay. So the dot product is the tells you if two vectors are pointing the same direction, it returns 1. If they're pointing in opposite directions, it returns -1. And if they're pointing at some angle to each other, it returns a number between 1 and 0 usually. Or so you can see the dot product that returns a scalar from a vector. You can see here I took the dot product and then I multiplied it by the normal vector. And so you can see I took a dot product of, I think, up. And so you can see as the vectors are 90 degrees at the equator, they turn to 0. We return to 0. And as they are pointing down against the up vector, we return -1. So they get flipped. And as they're pointing up towards the up vector, we return 1. So they remain the same. So it's a way of scaling vectors by the magnitude of their orientation against another vector and sort of sorting things in that way. So that in Houdini is, I don't think about it any other way than that. That is here. You see this vector. If I put a different vector, it's going to return something different. It's multiplying. And in here, you can see in here, I did a vector, dot product, and then I multiplied by the normal vector. Because the dot product is scalar, so it will not display as a vector. So you got to multiply it by a vector again if you want a vector. Okay, so I use the dot product quite frequently, but not in any other way other than to just figure out whether something is oriented in the direction that I want it to be oriented and return. And then I will multiply, like if it returns -1, I'll flip everything based on that criteria. So it's like a way of telling whether something is facing in the direction you want it to be facing. Okay. All right. Okay. So this is how we represent our velocity field again. But actually we don't. It's better to represent it this way. This is on it's called a staggered grid. So you separate the components where every and you'll see actually there's an option in Houdini to check or uncheck staggered grid. And that is because it's much easier to tell how much fluid is flowing into a cell if the vector is pointing directly into the cell rather than if it's at a funny angle. Okay, so then this is the data structure. There's a data structure that is the way the program stores data, and it's based on a grid. And the grid has a center, a face, a vertex, and there are face-centered grids, vertex-based grids, and center-based grids. Okay, and there's various advantages to each. And this is the one we use. It was called the Mach grid. It was invented in the early days of fluid dynamics. And it stores the pressure and the temperature at the center and stores the velocity values on the faces. And that causes some confusions in the way things are oriented. Why do I think that's interesting? Only because when you're thinking about how to store information and how to make a data structure, I think that's something that's sort of confusing a little bit from an architectural perspective because we're not used to relating space to just lists of numbers. And so if you think about the way computers work, usually like in the memory of the computer, it's faster if it just has a long list of numbers. And then you kind of keep in your mind how it's supposed to be organized. And that's how the algorithm is kind of written to situate it in the right place. So when you look at my code, you'll see things that are just, I'll show you in a second. This is the way the grid is organized, the staggered grid. Certain things are stored at the center, certain things are stored at the faces. and there it extends easily to 3 dimensions, and I have too many pictures of it. Okay. All right. So I don't know whether we will have time, but I want to begin to give you, I don't know how many of you are familiar with programming. I don't think we're going to be doing a lot of coding in this class. We might do one short exercise, but I think it's important to start the process in your life of being familiar with the vocabulary so that you can like read a brief snippet of code or something and try to understand how it works. For me, I have no formal education as a programmer. I simply knew enough to start reading code, and then by reading other people's code, I slowly was able to make little things myself, and gradually that built up into being able to make bigger and bigger things. So basically, when you make when you make a variable in the computer, there are 2 steps. The first step is the declaration, which is just giving it a name, what it's going to be called. And the second step is to allocate space in the memory for it. So you always see this thing where you always see a 2-part structure where there's like, it says double is the name of the data type, which is just a real number. And then it has a name. And then it says somewhere either right next to it or later, it says like equal to new double or equal to. So you can, this is like, I should have put this in the other order, but like, this is like, this is the declaration, this is the initialization. The declaration, the initialization. There's doubles, ints, bools, and strings. Strings are text, bools on and off, ints, integers. Those are the basic types. And you can declare them and then initialize them, or you can declare them and initialize them all together. Yes.
Is this C#?
This is C#, yeah. That's what I use. And so like, and then there are what we are using, what we're not using, but what we should be using if it was fast enough. This is a 2-dimensional array, so it's a list of numbers. It's like a gridded data structure. It's like it's got an index in both directions, an I and a J number that position the points in the cell. So that's a 2-dimensional array, and you can initialize it, name it, and then initialize it like this. It stores a grid of value. So it's easier if we imagine that we're working with 2-dimensional arrays. It happens to be that 2-dimensional arrays are very slow, so we kind of have workarounds for that. But essentially, there's a dimension in the X and dimension in the Y, and an I and J value locates a position in the grid. And you could have a 3-dimensional array, and then it would be an I, a J, and a K value that would locate the position in the grid. So basically, we iterate over all of the cells through each cell, and we do the operation on every single I and every single J value, basically. So I'll show you how that works, hopefully. And then there are other things, okay, besides ints, bools, and strings, and those are custom things that have been created with from these basic values. And Rhino has zillions of them that are this is the this is the point variable, and it has all these properties that you can access, and you have to create it in a certain way. You can initialize a point just like you could initialize a string or an int, and there's rules about initializing it based on how it's coded, but you can make your own, and then they have all these properties. So when you're writing code in Rhino, you just look up what you need to access the stuff that it already has programmed for you, and then you kind of just follow along with it. I'm not going to go into that. By the way, I'm using in our simulator, I'm using none of the Rhino geometry because Rhino is not meant for real-time simulations. It's meant for like displaying a thing. Okay. So this is an array at the top, a list of numbers, like a very, 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 very long multi-dimensional vector. Okay, and you can initialize an array with entering all the values, or you can initialize it with listing the numbers how much it's going to have. Like this says here, I said, make a new array, call it my array. Then my array is going to be equal to a new array with 10 values. Okay, so it's kind of confusing because you say the same thing multiple times, but this one just it names it, says there's going to be a thing called my array, but it doesn't exist yet. And then this one says now somewhere on the stack or the heap, there are two different places in memory. There's a place that has been created to store 10 numbers. And then you can access the numbers. Says the 0th number is going to be equal to 10. So this is where the index goes. This is the index that I'm saying, right? And here I said the 10th number is going to be equal to 5. So you make a placeholder for values, and then you go through and you can assign them by accessing their index in the series. I know that you're not going to be doing that yet, but it's if you want to look at the code, that's really all it is. Okay. Then there's loops. Loops look like this in C#. You loop, you set something that counts, and then it counts up to an amount. And there's all kinds of loops. I never use anything other than for loops because they're more stable and they're faster. I don't even know why the other ones exist. They must exist for reasons, but I don't know why. These are much faster and stable. So anytime something loops, it looks like this. And if you're going to loop over, a grid, you loop first through the rows and then through the columns. So that's like going through every number in a row and then going through every row in the column. Okay, so this is like all the numbers in a row, and then it goes to the next column and goes to, and then it does all the numbers in that row, and then it goes to the next column. Sorry, it does all the numbers in a row, then it goes to the next row, all the numbers in that row, then to the next row, all the numbers in that row, and loops through the grid like that. Okay, so basically in C++, you could just kind of like package this, and you could just say like for all values, and it would just do that. So anytime you see this, it really all it means is loop through all the values in the thing. And that's just repeated over and over and over again. Just for each cell, do these operations. So this is like standard thing. And that's what it means for each cell. And then there are conditionals. If this, do some stuff, else do that. And I think that's the entirety of programming, I have to tell you. Almost. Not quite. Most of the other stuff is technical things and like about syntax and trying to get it to work, or like there's complicated internal workings for stuff. But basically, I think conditionals, loops, and initializing and declaring variables, and then setting. Okay, so I believe that that is kind of the very basic. So I'm trying to keep it very short for now. Okay, so in our algorithm for simulation, this is how it works. Okay, so I think I said this once before, but basically I will try to explain, by the way, how this is connected to the Navier-Stokes equation. If I don't run out of time, this is basically a split version of the Navier-Stokes equation. So like that weird looking equation that I showed you in the beginning of class, like is not super, it has all these funny symbols in it. Basically, this is it splits it up into parts and executes it. And whether or not you can split up a differential equation into parts is one of those math questions that, you know, is that viable? That's the thing that it's only viable in certain scenarios, right? Okay, so first we add the forces, then we do something called projection, which is to make the fluid incompressible. Then we do something called advection, which is to move the velocity field due to itself, and then we move the quantities like temperature due to the velocity field. Okay, so why do I think this is interesting to go through with you? I have to say, I believe that the fluids are they're one of the most useful types of mathematical objects in the world. They connect to all sorts of computational and mathematical concepts. One of the reasons I'm interested in talking about this with you is a fluid is basically the analogy for all types of simulation and all types of vector calculus. So I think it's the example of things that people use to explain certain types of otherwise esoteric concepts. And so I feel like by going through the ideas surrounding a fluid, we can start to talk about some of those things. Okay, so this is from the Josh Stamm essay that I put up. This is this idea of self-advection. The self-advection may seem obscure, but we can simply interpret it as the fact that the velocity field has moved along itself. So these algorithms were originally written with a static velocity field to move smoke, which is called advecting the smoke. The idea was the smoke, like the value here would just get moved along the velocities. And then that is extended to move the velocities along the velocities. That's the idea of advection, self-advection, because it's a little strange because it's hard to think about velocity as a quantity, but that has to do with the difference between the Eulerian and the Lagrangian framework we talked about before. Am I making sense to you guys at all? At all? If I'm not, you should interrupt me, okay? Please. All right. So then this is the expanded version of the algorithm, okay? So add sources, add buoyancy. Then we have to extrapolate, which is, these are the names, by the way, which is deal with the edges, and then all this stuff, okay? So all of those things are the steps. And so these are, in my code, there's all sorts of other things, but these are the names of the crucial parts of the code. And the ones in gray are not really needed. They have options to turn them off. So these are the 4 parts to simulate a fluid, the most basic way to simulate a fluid. Add the buoyancy, deal with the boundaries, deal with the incompressibility of the gas, move the velocities, move things through the bullets. So I'll explain some things about that. So this is the first thing. This is this idea of extrapolation. So this is dealing with the boundaries. And if you think about it, if we're moving things in and around, if you're going to move something, eventually it'll move out of the simulation. Or this one here, where something might be flowing in, doesn't know what value should be flowing in. So the way that it is dealt with is there's a phantom cell perimeter around the border, and basically these values are copied to the outer rim. So that, like, this one is just set equal to that, this one is set equal to that, this one is set equal to that. So there's like a symmetry condition that's maintained at the border. And that, or you could set it to something solid. So this would just be 0, and then there'd be nothing coming in. And that is the way that the simulation maintains stability. And that is a little more complicated on the staggered grid. Okay, it's a little more complicated because there's 2 displaced grids for the different positions of the velocities. But essentially, it's the same principle. Why do I think this is interesting at all? I think it's interesting because the way of describing the world is constantly shifting between something extremely kind of delicate and specific and data-based and something extremely open-ended and experiential. And I think that I like the idea that we would build fluency in shifting between all of those types of methods of description. So I like the idea that in one moment we can make a film of some smoke and describe something. And then in the next moment we can talk about, like, how do we copy values from one cell to another? I think the fluency to cross those boundaries is something that architects have and that no one else really has. And so I think it's valuable for you guys to gain, to experience all those different ways of talking about things. Okay. So then I have made like little snippets, by the way, of the code that I've written in here. And these are not exactly the way it's written in the real one. They are sort of simpler versions of it. I took out some of the things that make it confusing to read. But basically, this is the thing that states the name of the function, extrapolate. This loops through all the values on the border. This copies the value. And I'll go through some of this in a minute, but basically this is just a way of calculating the index, and it's just copying the values. Okay, that one's a little confusing. That's why I did it first. All right, then there's something else. I mentioned this before. You see this thing in the code a lot. It's always called I2X. And it has this thing and it makes it confusing to read. Basically, it is about simulating a two-dimensional array with a one-dimensional array, because one-dimensional arrays are very, very, very fast, and two-dimensional arrays are very slow. So if you want something to run in real time, you have to do this workaround. So basically, if you think about it, you can imagine that you have a 2D grid, and you can just store a list of numbers, and then you can write it as though you're entering the position in a 2D grid and have a little formula that calculates where that position would be in a one-dimensional grid. So and the formula is this: I plus the nx, which is the size of the grid, times j is equal to the index. So an example would be if I want to find position 2, 3, column 3, that's j3, and I2, I can say 5, which is the length of the side, times 3, which is j, plus 2, gives me 17. So I can basically find positions. I can have a big long list of numbers, 0 through 24, but I can access them as though they are a grid, even though they're not. And that's just for my human need to know that if I want to say, if I want to call the neighboring cells to this, I would want to say 2, 2, 2, and then 2, 2 plus 1. I would want to say 2, 3, 1, 2. Does that make sense? I should have written on this is ij, this is I plus 1j, this is I minus 1j, this is I plus 1j, this is j plus, sorry, I'm screwing it up. Do you understand what I'm saying? This is the grid, this is ij, this is ij, this is j plus 1, ij plus 1, this is I plus 1j, and this is I minus 1j, and this is I j minus 1.
So I is just the index for the
I is the index for the x, and j is the index for the y in the grid.
So what's the value? Is
Yeah, it's a little confusing. Basically, it's very. I'm just trying to make it so you can read the code. By the way, this is not there's a very normal way of. It's very abnormal to have a two-dimensional array because they're very slow to actually have a grid stored in the memory of the computer. You want to just store all the numbers, but for our own intuition, we want to be able to say, since I need to explain. I'm going to write on this. This is nx. This is these are the I indexes. So 0. This is I equals 0, I equals 1, I equals 2, and then this is j equals 0, j equals 1, j equals 2, j equals 3, and j equals 4. And so then I can call a cell with an I and a j. I can call it with an I, I can call it with a 2, 3 would be the index of this cell. It's not the real index. The real index needs to be 17. So I have this little lookup form.
But pretty much, you're taking a 2D array, you're treating it as just like a list by flattening each.
That's right.
You're just shifting
exactly.
each of the row like that.
Exactly.
And then you're
stacking them on the end of
you
each
get
other.
Like this. You're given the two indexes that correspond to x and y, and that formula will just convert it into an index that corresponds to that thing in the list.
Thank you. So incredibly clearly said. Wish I could speak like that. Yes, that's exactly what I'm doing. Okay, and that is just because in order to simulate something, you have to use one-dimensional things because they're much faster. So you'll always see this little thing with all this extra little information, and that's just saying look up this particular number. Okay, and this is how it is said by Josh Stamm. If you're interested in how he said it, it's just another version of it. Here is his define. He defines this little macro to look up the single dimensional array value. Okay, and so this is the buoyancy calculation, incredibly simple. This is what's called pseudocode, and this is the real code. Pseudocode is the algorithm, and then this is the real code. So it just says for each cell ij, the buoyancy force is equal to the value we enter for buoyancy. That's what you're entering in Houdini, 1678 times temperature minus the ambient temperature. And then we update the vertical velocity with the buoyancy force times time step. That's it. Like, so incredibly, there's all these words and extra lines, but basically for each cell, add a buoyancy in the vertical direction. Okay. And then that's the actual version. Here's the for loop, double for loop. Here's the look up the actual index, then calculate the buoyancy, and then update that particular cell with its index. So it basically will go through every single cell and do this. This one, it'll calculate the buoyancy force and by taking the temperature of the cell. So it needs that, you can see it says temperature index. It looks up the temperature of that cell, subtracts the ambient temperature, multiplies it by the buoyancy force, and then updates the velocity of that cell. It does that for every single cell in a row. Okay. And that's why we need these indexes. I hope. Okay. Now, this is the start, I think, of the interesting part. This is the main kind of crux of the algorithm, is this thing called projection. And this has to do with vector calculus. It's very beautiful entry point into vector calculus. So I'm actually going to do the vector calculus towards the end of the lecture and do this part first. I don't know if it's the right order, but we'll try. Okay. This is a vector field where there is divergence. We need the concept of divergence. It's something called, and divergence is a property of a vector field. It's one of the main properties discussed in vector calculus. This is positive divergence, and this is negative divergence. And that is, the concept is, if this is a fluid or a magnetic field, stuff is flowing in here at an incredible rate. This is like a sink. You can imagine it like a drain. There's all this fluid just pouring into that. And over here, everything is coming out. It would have to be a source. You'd have to imagine like a hose pumping in water here. So like, basically, anytime you have something moving, the degree, anytime you have an arrangement of vectors, the degree to which at any one spot stuff is pouring in or flowing out is called divergence. So like, this is a huge divergence. The divergence down here is kind of like zero because everything's just flowing along. And this has a massively negative divergence because that is all the fluid is pouring in there. And so every vector field has this property. And you can ask of it, if I look at this spot, is there more fluid pouring in or more fluid leaving? And in the case of magnetism, there's always positive and negative divergence, right? Like this spot is pushing out, this spot is pulling in. And in the case of, that's basically this. Positive divergence like an explosion or a source, and negative divergence is like a drain or a sink. And so that is like this. that is written, the symbol for divergence is that is written, this is a symbol, it's called del or nabla, written nabla dot, and then the vector field name. And if nabla dot or del dot v is negative, you have a drain. And if it's positive, you have a source. And if it's zero, you have an incompressible fluid where everything's just flowing along naturally. So the main criteria in the Navier-Stokes equation is what's called the incompressibility condition, which says that the divergence is zero everywhere. If it's not zero, stuff is getting smushed or expanding out. If it's zero, it's just flowing along. So we have to enforce incompressibility, or it doesn't behave like a fluid. It'll behave like a magnetic field or something else. Or it'll be like an explosion. And in Houdini, you can change the divergence, and that's because you want to make an explosion. Or you want something like magic effect, where something gets, like a guy gets crushed or something. Okay? And so, basically, you can look at any cell, and you can say, you can add up the flow that comes in and the flow that comes out and calculate the divergence. Okay, so like the only tricky thing is you have to be careful of the signs, because flow in here is positive and flow out here is positive. So like it's not exactly just adding, but that's the negatives and the positives just have to do with the fact that that is flow out is negative and flow out is negative. Flow out is positive, flow out is negative. So the divergence of it, yes?
Is this a staggered cell thing? Or
yeah, this is staggered cell, but it's universally applicable. This is basically is the discrete version of divergence. So like we always talk about like there's differential geometry, differential calculus, partial differential equations, and there is discrete differential calculus, differential geometry, and partial differential equations. Discrete means broken up into little chunks. And computers are always operating discrete mathematics. So like basically if you have a tiny little cell of space, the divergence is just the amount. But yeah, you're right. You're right. This is because I'm using the staggered grid that I can calculate it so easily. If I had arrows coming in all sorts of weird ways, I'd have to break them into components first and then figure out, how much was, if I had like an arrow here, I'd have to break it into two components and use the vertical component. Okay. Okay. By the way, I have to say it's a little dry. I understand, but you have to believe me. Like it's so incredibly, stunningly beautiful that something like a fluid and something like a box share these properties. And you also have to understand just how incredibly you guys are tired and you're working and you have all these anxieties about being students. But you have to understand just how incredibly brilliant you all are and how much you can do. And so it's important to me that you know that someday you might be able to do vector calculus if you want to. Okay? Because it's not that hard and you guys can do anything that you want. And it's important that you build a foundation of fluency across multiple disciplines, or at least that's my perspective, but I don't know. Okay, so this in the staggered grid, you're correct. This is a source. There's more going out than going in. This is a sink. Too much is going in. And then this one, mass is conserved because the same amount is flowing out as is flowing in. So the projection algorithm, the crucial step in any fluid simulation is to enforce the incompressibility condition and make sure that you correct all the velocities all across the system so that mass is conserved, and don't let anything be a sink or a source unless specifically targeted that way. Yes.
Question.
Yeah.
First is why isn't the why is the blue arrows always in the same direction for all three?
Oh, I just drew these arrows. Like it's not like I'm just saying like in this one, there's two arrows. These arrows are all the same length. So in this one, 2 arrows are coming in and 2 arrows are going out. So they're equal. This one, I know these are all the same length. So this vector and this one have the same size as this one and this one. So this is like 2 going in, 2 going out. This is 1 going in, 3 going out. Too much is going out. This is 3 going in, 1 going out. Too much is going in. So I just made them all the same length, just to like as a simple representation. But actually, like in the real simulation, they'll be all different sizes and lengths. But the thing is, we have to go through every single cell and say, what's the divergence here, and then set it equal to 0, so that the thing is behaving like a fluid.
My second question is,
yeah.
So does this represent one cell, or is it like in between, like is it like in the middle of like 4 cells, or?
Yes, there would be like this cell. That's right. So like it would be like that. Although all these arrows would be different sizes. It's like a giant grid, and there's flow going in to every single cell, and we have to basically calculate whether if you imagine you have a velocity field like with a bunch of cells, and you update all the velocities, so like it's all incompressible, and then you move all the velocities around. Now some of the cells have too much going in and some of them don't, and then you have to have another step where you go through and you correct it all through every cell. So I would ask, let me find one that they're not equal. I think I have one. I thought I had one. Like, thought I had a drawing of this. Like, yeah, there would be cells. There'd be cells here and here and here. These would be like next to each other. It's a single cell in a giant grid, and every single one is going to have, after I update the velocities, is going to have too much velocity going in or too little, and then I have to go through and make sure that they all have 0. And obviously, it's very tricky because if I update one, it screws up the next one. Right.
So like, I just wanted to ask, like, these 4 arrows don't really correspond to this one. Like, 1 arrow belongs to 2 cells at once.
This is just a diagram of the divergence in a single cell. This is just like this diagram.
I was just like wondering, like, arrow doesn't. There's no cell that like exclusively like has its own arrows. Like arrows.
You're correct. You're absolutely right. There's only 1 arrow attached to every face. There's not like a separate arrow for this one. Like this, if these in reality would be next to each other, and this would be a shared arrow.
Okay.
So it's like the 1 arrow represents flow out and also flow into the neighboring cell.
Okay.
Like it would be like I think like
But this only occurs for the staggered cell representation. So the arrow is in the middle, right? So it only belongs to that cell, or that doesn't matter.
Yeah, although in the other version, like if you imagine there would be an arrow here, it would be like that, and then I would have to break it into components, one going that way and one going this way, and then this one would be going into that cell, and that one would be going into that cell.
Oh, so it doesn't like spread into the 4 sides. It like only spreads. Like you have to like choose a direction that prioritizes.
Well, because I'm gridding the universe, like orthogonally, I can make this approximation. Like, but basically, there would be velocity stored at the center. You're right. Okay, like I don't know how to say it. I wish I could draw on this stupid thing. I knew that this is like too far away for me. There would be velocities stored in the center of the cells, and then there'd be a velocity here and a velocity there. This one has a horizontal component and a vertical component, and so does this one. So it's the same as storing the velocities at this here, except that I don't have to do this step of breaking them down into of decomposing the vector. And also that I actually don't know the velocity at the middle of the step. I only know, like, I actually don't have a velocity. Too confusing, but like, there's a problem with storing them at the edges, which is if I want to know the velocity here, I can't just take these components, combine them, and have a.
That was my concern.
Yeah, you can't do that. You have to interpolate.
So it's like you can. So I'm just saying, you convert from the previous data structure to this data structure. You can go forward, but you kind of like go backward. Coming.
They're just separate. They
Okay.
can't be
They're not like compatible.
the algorithm would be the same. The use of it would be the same. Like, because if I wanted to know how much flow was going into this cell from this cell, I would just decompose the vector and take the x component and say that was the flow going into this cell.
Okay.
But I can't take these two components and say I have a vector here that looks like that. And I can't take these two components and say I have a vector there and a vector there. Because they're not stored, like the velocity is pretending to be continuous, even though we are only looking at it at these particular spaces. So like the idea is that we are not storing, the idea is that we are pretending that between here and here, the velocity is in between. We just don't store that information. So if we want to calculate the velocity here, we would do what's called linear or bilinear interpolation. So we would average all the neighboring velocities, and that would tell us what it is. So actually, when I want to move the temperature, I do that because the temperature is stored at the middle. So when I want to move the temperature, you bilinearly interpolate between all the neighboring velocities to get the velocity at the center, and you use that to move the temperature. So there's an extra step there, and it avoids decomposing the grid in this step every time. I'm not sure, honestly, that the staggered grid is better. I have debated it. Like, I've tried both ways. I just I don't know. Like they each have an inefficiency somewhere. So then the issue is this: if you remember that fluids can't push in a direction. So I can't just say, like, if there's too much flow going into this cell, I can't just like add more going out there. I have to add more equally to all four sides, because fluids, like, they can only push out. That's the definition of a fluid, is that it can only push out. Because it can't resist shear forces. It is what makes it a fluid, that it can only do this. That's Pascal's law. And so, like, what I need to do is basically figure out the divergence, divide it by 4, and then add little amounts to every single direction. And that looks like this. This is the pseudocode. Now, the thing is that you can't actually, if you just went through and did it once, it would still be, it would screw itself up again. So basically, because this one would be good, but then that one would get messed up by this one. So, like, you know, if I did this one, and then I keep going, the next one messes up the one I just did a little bit. So I have to do it many, many times. I have to have another loop that does it over and over and over and over and over again until it converges at a solution. So it says for a certain number of iterations for each cell, calculate the divergence, divide by 4, and then subtract the difference from the velocities in each cell.
How do you divide by 4?
Because it's got 4 neighbors. 1, 2, 3, 4. So, like, the divergence is how much extra is flowing in or out. Divide it by 4, and then I add that to every single side.
How do you know how many times to, like, iterate it before it converges?
So there's you don't. But, like, if you look in fluid, in like ANSYS or something, or OpenFOAM, there'll be like a little monitor, and you select certain quantities, and to see how far they are from 0, and you watch it, and you just watch the graph, like, and when the distance stabilizes, then it's converged. So, and they never converge. There's always error. So they just like they converge as far as they will.
Close enough and just.
Yeah, although in this case, it's not, there's few enough cells and it's not, so it actually will converge. I don't understand that completely, by the way. Convergence, whether an algorithm converges or not, is like, it's like a whole type of analysis, right? But like, what I'm using, okay, this is the actual code, okay, is something called Gauss-Seidel. This is another one of those things. We talked about the Newton-Raphson method. This is Gauss-Seidel. And then there's the other one is called the Jacobi method. These are like the two methods. So Gauss-Seidel, like just to illustrate it, basically like it's a way to solve a system of equations. So basically you solve the equation for each variable. This is the version of it in math, right? It's not the version in the computer, but by the way, it's very confusing. One of the things I think is important about this way of thinking, by the way, it's an important thing. There's always like a thing, like this is like a method. But then if you read about how the method works, it's always the description is on some other thing, some sort of theoretical example. And then the actual version of it is never quite exactly like that. It's kind of applying it in a much more practical way. You know, you could just imagine. Let me try to explain. Okay, so in the abstraction, like basically I have three equations with three unknowns. I solve the equation for each unknown. Then I pick a random number, plug it in, and then I calculate. I figure out if I chose all these random numbers, what's the first value, and then I use that value and the two numbers that I chose, plug it into the next one. Then I now know what a new x2 is, and I plug that into this one. And so like I basically gradually it gets more and more and more accurate. So like it's much easy. Actually, the Jacobi method is a little easier to understand because I do it in three rows. So in this one, I say they're all going to be zero, and I solve for each one. And then I say they're all going to be the new values, and I solve again. And then they're all going to be the new values, and I solve again. And in the Gauss-Seidel, it's progressive. So like I solve for x1, and then I plug x1, the new value for x1 into x2. Then I plug the new value into x3. So like there's sort of a difference in whether or not the difference would be like if I calculated the divergence across the entire group of cells, and then I updated, and then I iterated again, iterated again, iterated again, iterated again, and then at the end subtracted that from the velocity, versus if I'm constantly updating as I'm calculating. So like in practice, there is an equation, okay, and the equation is that one for the divergence. This one. This has to be equal to 0. So, and there is a version of this equation for every single solitary cell, essentially. And so basically I have however many equations as I have cells. And that's what it means, like when you see it, like this is an example with 3 equations. But in actuality, there are, 13,000 equations, basically, however many cells there are. And so the idea is that it's trying to converge towards a solution for all of those individual equations for divergence equal to 0. So it is actually exactly this. There's that divergence calculation and I start out by just saying it's whatever it was from the last iteration. Or sometimes you automatically just insert values. But basically, I update the velocity. I just calculate it. It's some random value. And then I iterate it over and over and over again, setting those equal to 0 and updating for all the other quantities. So I've got 13,000 equations. And those equations, like you essentially set them equal to 0 and run the simulation, calculate it again and again and again. And basically, in a simple scenario like this, the numbers will converge. In a situation with 13,000, they might not converge as quickly. And often those are written in matrix form. So like if you are actually doing this, they'd be written in this format. Okay, and then if you want to have obstacles, it's very easy. Like all you have to do is divide the divergence by the number of empty cells rather than by 4. And that's okay. Now this is it's very beautiful, by the way. This is allowable only because of something called the Helmholtz-Hodge decomposition, which is like an idea from mathematics, which says that every vector field in the world is the sum of an incompressible field and a gradient field. And so basically, if you think about it, we are calculating the gradient field, which is I haven't talked about yet, but like essentially what we're doing is the gradient field is like another thing like the divergence. It's another operator from vector calculus called the gradient. And the gradient is the direction of steepest ascent or descent. So in actuality, you need to not do it the way I did it. You need to do something slightly more complicated, which is you need to actually not solve the equation that I wrote, but you need to solve something called the Poisson pressure equation, which is the same. Okay, it's just like it involves like a much longer formula because the real question is how does the pressure field correct for the velocity field? And so there's an idea that some random velocity field is always equal to a divergence free field and a field of maximum flow beat. And so you can write another equation called the Poisson pressure equation, which is this. That's what it says. The gradient of the pressure, some new velocity field, some corrected velocity field, is equal to the velocity field that we have minus the gradient of the pressure. I haven't talked about the gradient yet, but the gradient is another thing like the divergence. If you think about a velocity field, or like it's like there's a direction of maximum slope in a velocity field. Like the velocity field is kind of like, you imagine like a hill pouring water on it. The direction the water runs down the hill is the direction of maximum slope. And so this is the rigorous version, is to subtract is to use this relationship between velocity fields and subtract the pressure to get a divergence-free field. And it's slightly more complicated than the method that I use. You need to solve this. But it's the same, basically. That equation is not as confusing as it looks. It's just a longer equation than the one that I solved. Right now, it has nabla symbols in them and everything, but I promise you guys, those symbols it's just like saying, like, plus. It's the same. It's just a notation for like a particular operation, like plus or minus or division or multiplication. It just means do a thing. to the values. So they look confusing, but it's just a longer equation than the one I used, which is just subtract the divergence. And then you can do the same Gauss-Seidel iteration to solve the velocity field. Okay. All right. Are we okay? Everybody okay? Okay. This is the last part of the algorithm, and then I want to move on to some of the other things. Do people need a break? Do you need a break? All right. Let's take a 10-minute break. Okay. Okay. All right. All right. We can take a break. I just wanna get through it all with you guys. Okay, and then we can take a break. All right, so this is the stupid thing I mentioned to you guys before. Forward Euler. You remember I said that? It's so lame. Okay, but it's not. Okay, this is the idea. Okay, the idea. This is so cool. I have to tell you. Okay, one of the coolest things in the world. I think it's the most useful idea that I've discovered in the last 10 years. Okay, this is forward Euler. You have a point. You multiply the velocity times the time step, and you move it forward. But we're not really moving points, we're moving quantity. So like if this temperature is like 79 degrees, after one time step, we now should know that the temperature over here would be 79. That's the idea. We know the temperature was 79 degrees here. We know the velocity field of the water. It moves the air. It's moving this temperature. Now this spot is 79. So we update the quantities in the field by using the velocity. The thing is that it's like this. Like all of these would be moved. And then we would have a bunch of numbers floating in space. And now it would be difficult to figure out what the value was at the grid center. Like we wouldn't know how to do that. We would have to look at all the near ones and measure their distances to the point and average, which we could do. That would be fun. The thing is that over time, it just so happens that this is unstable. Like, because what happens is you end up with a lot of averaging. And so over time, the quantities deteriorate. It becomes blurry over time. And it turns out, by the way, this is just a miraculous thing. No one knew that this was going to be the case. It just happens to be the case. We use something called backwards Euler. Backwards Euler, we pretend we're one time step forward, and we try to figure out where that value has come from. So instead of moving a value forward, we look back. We say, if we're going to be here at the grid center, we look back in time, we figure out what value is going to come here, and then we move it there. Okay, and so basically we look at this point, we move backwards by the velocity, and then we have 4 neighbors, and we linearly interpret to figure out what that value is, and then we move it to the new grid center. And this method is more stable. Okay? And I think this is something I really have been wanting to tell people for a long time. I believe this is a fundamental distinction. It is incredibly beautiful that being in the future, pretending you're in the future, and looking into the past to where you came from is more stable way of going about things than looking into the future and trying to figure out what direction to go in. And this is the distinction that I had when I was a young person in pursuing my career versus now. Now I just pretend that I'm where I want to be, and I think about what I did in order to get there. And when I was younger, I used to wonder, what do I have to do to get where I want to be? And if you're doing the second one, it is unstable. You wander around in different directions. if you assume you're going to be able to do the things that you want to be able to do, which all of you will, every single one of you will achieve exactly what you wish to achieve. You assume that if it is your base assumption, you will be successful in all the things you want. It's much easier to ask the question from that point of view, what did I do to get here? Rather than to wonder, what do I need to do to maybe achieve the things that I want to achieve in the future? You have to assume you will do it because all of you will, and then just follow the steps. Okay, so backwards Euler your life. Okay, now we can take a 5-minute break. Okay. Yeah, the 3 ways to improve accuracy, 4 ways to improve accuracy. Change the interpolation scheme, use a higher order advection scheme, increase the grid size, or decrease the grid size, or decrease the time step. And then basically linear interpolation is like this. You find the average of those values, and the average of those values, and then the average of those values, like a weighted average. So you figure out the x value, this one, and the x values of all the neighboring points, and you subtract them to get a weighted average. First you do that with those two, and then you do it with those two to find the value there. And it's actually like a little complicated, like because there are different algorithms for the linear interpolation, but essentially it's a weighted average of all the neighboring points. So this is the pseudocode for the advection algorithm. So you say for each cell, you get the x and y value at the cell center. And that seems like we should have it, but actually, if I were to use Rhino would allow us to store a point at every one of these spots. But the point has all sorts of extra data. Like it knows all these other things about itself that we don't actually want. So it's much faster if I just know I'm looking at cell ij and I know the step h and I know the number of cells in the grid, and I would set I would every single time calculate the value at the cell center by multiplying by multiplying the number of x by the number of y times the h. So I would do like x here is equal to h times I plus h times j plus h over 2 would give me like the value at the cell center for x and y. And then because I'm storing things in a staggered grid, I have to bilinearly interpolate to get the value of the velocity at the center. And then I use backward Euler to figure out where it came from. Then I bilinearly interpolate at this spot to figure out the value of the density there, and then I move it forward. And the other thing is that you have to store all these values in temporary storage, because I don't want to start looking and finding the values that I've already updated. So that is the algorithm, and this is that's what it looks like. So it says for all the rows, for all the columns, find the index, calculate the x value, calculate the y value, bilinearly interpolate. This is a separate algorithm. I spent a long time worrying about different bilinear interpolation, but you don't really, this could be substituted out, right, with a different one. And then you use backwards Euler, find the previous x, which is x minus the time step times u, the previous y minus the time step times v. And then you bilinearly interpolate again with the previous values and set that equal to the new value. So all of this only says that this is called Edbeck density. It takes two fields and a time step. Okay. All right. I hope I can do this. All right. So remember, talked about this many times, this stupid animation I probably showed before. This is the derivative moving 2 points together very slowly until they get so close together that we can calculate some quantity. This is, in this case, the way you do the slope in computers. This is the formal definition of the derivative. I don't know if you guys remember this. This is the function plus a little value minus the function at the old value divided by the little step in the limit as the little step goes to zero. Right? Everyone, by the way, you always have to do this. Anytime you invent something, somebody has to do the formal definition. I never pay attention to it. Okay. And then but that's what it is. And then the partial derivative. This is ridiculous. Okay. This is like a whole multiple levels more difficult. Supposedly we have to do 8 subjects before we can do this. But I don't find it that different, honestly. It's just so I don't know if this is if it's a good idea to talk about. Usually you do ordinary differential equation before you do partial differential equations, whatever. But it's not that confusing. I think the whole world pretends to be too confusing. Like constantly, everyone's always trying to make it seem like every field is very opaque, and it's not. Usually, the realizations are not as complicated. Okay, so that's the formal definition. But basically, the partial differential equations is what we have to do on these fields because they're vector fields. So you can't do ordinary calculus on a vector field because there's 2 variables. So we have to talk about this for a second. This idea of a function. A function is this, right? It's an independent variable equal to some expression of dependent variables. And one of the confusing things, I think the confusing thing about reading mathematical academic papers is that they refer to everything as though it's a function, and nobody ever knows what the function is. Because it's not really a function. They're talking about measuring some quantities in reality or some field that's been updated by some other algorithm. It's only referred to as a function because that's the notation that we have. So basically, when you see this, it's usually in math, the concept is defined on a known function. But when we're talking about something in the computational realm, it's just a bunch of values that have been found in other ways. There's no expression that we're evaluating. We just assume that it's there's a set of relationships in space, and we call that a function. I don't know if that makes sense. Like basically, one of the things I find most beautiful about this way of thinking about the world is that really the language of math is just about describing relationships between things. And you can say if I have a relationship between 2 things, I could imagine that looks like a surface, or I can imagine it looks like a graph, or I can imagine it looks like a fluid, or I can imagine it looks like a vector field, or I can write an expression for it in that's an approximation of it. But really, there's no really, like when you see, like one of the things I like about the geometry class is, we're doing all these funny surfaces, but actually those surfaces could equally well like describe the relationship between rabbits and trees or something like that. It's not really, there's no real division between the three-dimensional world and, relationships between ideas. You can graph, how many people came to school today as a surface. So if you can use the language of mathematics to describe any set of relationships, and vice versa, you can use three-dimensional world to visualize any set of relationships. So somehow there's a way in which there is a deeper possibility for how we could describe architecture, in terms of thinking about the three-dimensional position of the walls in the same language that we use to describe the way people are moving around in it. I find that powerful. Okay. There are also vector functions. Okay. A vector function is a function that returns a vector. So this is a function of two variables. Usually we think about a function of one variable with one input. This is what you can do normal calculus. Have a function with two variables, x and y, two dependent variables, you need differential equation. This is what you do in calculus 1 and 2. You have two input variables, you need a little more few extra concepts. And then there's also functions that return a vector rather than returning a single value. They return two values or three values. Really, it's just two functions, but you call them this, okay? And that is quite lovely. So this is a scalar function. That's a function of two variables that returns a single value at every point. Okay, so and you can graph that as like a color. I hope. By the way, every time these graphics, I've uploaded the scripts for these things. Okay, this is a vector field, and that's a function of two variables. So it takes place in a grid, and it returns two values. And we can imagine that those values are arrows. So it's one way of a vector field is one way of representing a function that returns two values. Okay, so I have, by the way, just for practical, it's very annoying to me when I don't know how something is made. So like I have like grasshopper scripts of all the things that I'm showing you. Okay, so like this is the vector field like script. Basically, like there's a bunch of x and y values, and there's a function, and it is evaluated. I should have this up here next to this one. There it is. A function and another function. These are these two functions, and they're evaluated at every x and y. And then the x and y values give us points, and they also give us these two outputs, which can be packaged as a vector. And then we can display those vectors at every point. So if I were to change this function, right? Okay, so or change the number of points. Okay, so this is all it really means, is that at every point in 2D space, at every x and y value, there is two values that come out. But that's also like saying I'm mapped, that can be pictured as in the 2D plane, but you could also picture it some other way. It's just like saying I'm inputting two values and getting two values out. And one way to look at it is as a vector field. I love that it's just that the vector field is a way of looking at it. Oh my gosh, I'm all the way at the beginning again. Okay, So, by the way, typically in a vector field, the vectors are very long, actually. And the way it's usually displayed is they are scaled down dramatically, and then you can use color or some kind of other map to map the values. So that's what I've done here. If you look, there's a scaling factor down here at the end. Like if I were to make this, they'd be super long. And then I'm using a gradient to color. Okay. So this is a vector field. Yeah.
What's the A times B?
This,
No, B.
this.
Yeah, what is that?
That's a scale. That's a multiplier. Just multiplying the vector by a value. It's just scaling them down so that they display more accurately, more visibly. Okay. It's not. This is just what Grasshopper calls multiplication. It's just multiplication. Just multiplication. There's nothing special about it. It's just multiplying the vector by a number. So vectors have magnitude, and if you multiply a vector by a scalar, it'll just scale the vector along its length by that number. If I were to multiply it by another vector, that's when I would have the cross product. So it's very confusing, by the way. I get confused about this all the time. Like if you multiply a vector by a scalar, it just scales. If you multiply a vector by another vector, that's when you have to do the dot product or the cross product. Yeah.
Why do you reparameterize the vector?
I unitized it. Oh, actually, you're right. I scaled these all uniformly. There they are. That's the real sizes. Look at them. Huge. Okay, isn't that hilarious? So this is what I did here is I took the maximum and the minimum, and I used the maximum and the minimum to generate a color field, and then I unitized all the vectors and set them all equal to a size and mapped the colors on. Yeah, when you unitize a vector, basically you have a vector like this. When you unitize a vector, it sets the magnitude equal to 1. So like it scales it so that magnitude is 1 along the direction, and the components are appropriately scaled along that angle. So I almost always unitize my vectors that I'm working with, because really I'm just trying to figure out what direction something is pointing in. I very rarely or you can also do like a length. You can do like this vector length, and then that will give you the length of the vector. And then I could also do a vector deconstruct, and I can get the x component and the y component and the z component. Okay, so this is a standard way of doing this. Basically, you have a range of values, they're plotted, and then you use those to mark a point and evaluate a function for a vector. And then this is all display. And then this is the scalar field, which is the same, except there's only one function as opposed to two. And then that function can just be plotted as a color. This is scalar field and a vector field equation. And then also there's a 3D vector fields, like something like that. And that is a function that returns 3 variables. Vector fields, by the way, are typically functions that have the same number of inputs as outputs. That's what we typically plot as a vector field. And that's because it's taking place in 3-dimensional space, and it's giving us an arrow in 3-dimensional space. So if it has the same number of inputs as outputs, we typically call it a vector field. I think it's beautiful because there are just ways of thinking about the world, like you said, Miles. It's not one way. It just happens to be that this is a good way to display these. So if you look at that, this is the same algorithm, except now there's 3 values that are generated, and then there's 3 functions that are evaluated, and then those values are packaged as a vector and plotted. Yeah, they're all going to be in a folder called scripts. Okay, so every single, and so will the Houdini ones. Yeah. And I can extend the domain or whatever. Okay, so this is a 3D vector field. The reason for that, by the way, is I hate when somebody shows me a picture and I don't know how it was made. It feels frustrating. By the way, functions are also, you can also think of a function, a 1D function this way, as a transformation. Basically a map of a bunch of values in one space into a different space. The animation has nothing to do with it. The animation is just a visualization of it, okay? But this is a 1D transformation, since there's one input, x, and one output. So they can be represented as scalar on a number line, like that. That is also uploaded, or will be. And then if you, a vector field can also be represented as a 2D transformation, where you are taking a bunch of inputs and can repositioning them in space. So this is called this is a non-linear transformation. If these equations were linear, meaning they didn't multiply by themselves, that would be the domain of linear algebra. And linear algebra is what governs shearing and projection and translation and all the things that you do in Rhine. So a linear function is one where straight lines would remain straight lines. These you can see are distorting into curves. And that's because this is a power. There's a multiplication in the function. Okay, so just the point is only that is also a vector field. You can also look at it this way. So relationships can be looked at in many different ways. And by the way, a parametric function is also a transformation from a plane into 3-dimensional space. So the number of inputs is how many dimensions are in the starting space. The number of outputs is how many dimensions are in the resultant space. So a parametric equation has 2 inputs. It's 2D in its own mind, and it's 3D in its output space. And that, you guys have had these kind of scripts for years. It's just, I'm just saying this is the same idea from another perspective. Okay. So the normal derivative is written df over dx, or df over dt, depending on what is the independent variable. So if it's a function of time, it would be df dt. If it's a function of space, a single variable in space, it would be df dx. That means a little change, a tiny little change in the output over a tiny little change in the input variable. When you're talking about partial differential equations, the symbol is not a d, it's this little, like, whatever it is. What is that symbol? I don't know. It's like a little, like, Greek d. Okay, that's the symbol for partial differential equation, and this means it's a 2-variable function or a multivariable function, and we're just differentiating it with respect to x. So what it means is, like, you pretend that all the other variables in the equation are constant, and you differentiate with respect to the only variable that remains. That's how you do it. So I'll show you that in a second. Basically, it's like slicing the function with a plane and differentiating the intersection with the plane. So it's like doing that. You basically intersect this is a function of two variables. How do I know that? Because you can imagine it like a height field. It's like every point in this two-dimensional plane is outputting a single value vertically. So I'll show you that in a second. But one of the ways you can model an equation is like every point in the plane has a scalar output, and rather than modeling it like a gradient, you can just model that output as the z value. That makes a surface. You can intersect that surface with a plane that gives you a curve. Then you can differentiate the curve normally. So that looks like this. Here's the original function. Y equals x squared. I pretend that y is constant. I differentiate normally. Then I pretend that x is constant. I differentiate again, and that gives me the partial differential equation with respect to x and the partial differential with respect to y. Okay, so you just pretend this doesn't exist, and you use what you already know. Okay, and that looks like this. So I will explain this in a second. This is the equation for z. This is z, or f of xy is equal to y x squared. And then if you imagine intersecting this with a plane of constant y, and then you differentiate the curve, you get an equation, and that's the equation for that for the slope. So okay, so there's this is here as well. This is called equations implicit plus partial div. Okay, and so this has a number of parts. So this first part, okay, this is the equation. So it's done the same way. Basically, there's a bunch of x values, a bunch of y values, and then there's an equation. And that is mapped into a bunch of points. The z value is the result of the equation, and the x and y value are the inputs, and then you can map those in 3D space, and this little thing makes a mesh out of it. Okay, so that is that is not a parametric way of modeling a surface. It's what's called an implicit equation, because it's just a relationship. It's just df of x is equal to x squared y. And so I just evaluate this and plot this as the, actually, sorry, that's an explicit way. Okay, so that is that. Then this little portion here just draws a plane. This has nothing to do with anything. But then what is cool about the way that I set this up, okay, that's the differentiated version with respect to x that I just showed on the previous slide. That's this 2xy. There it is. And then if you want to evaluate this and draw the curve, basically this is the same function up here. This equation right there is the same equation. And then instead of doing it, I'm doing it over all the x values, but with a constant y. And that gives me the points along a curve. that is the intersection of the plane that would have that constant y value. The equation of a plane is just like y equals 5 or whatever, because it's all the values where y equals 5, right? So this is like the equation of a curve, the same equation that modeled that surface with only with a single value of y is the intersection. And then that's drawing the curve through those points. And then this is the partial differential equation for this, for a constant y. And so if I evaluate that at a constant y and a constant x, which is a point along it, if I evaluate the same function here at a constant x and a constant y, it gives me a single point right there. This is the same function that I did for the whole thing. If I evaluate it now for only a single x and a single y, it gives me a point. And then if I evaluate the partial differential equation and I have to make a vector where this gives me the slope, right? So I can just make a vector where I say, like, it's in the plane. So it's like y is 0, x is 1, and then z is the slope. Like, that would give me, like, a vector, like, like that. And that is the equation, that is a representation of the tangent line. And then down here is the other one for the partial differential equation with respect to the other way. And it looks like there's I think something wrong about this. Something's wrong about this. I'll fake that line is wrapped in the wrong spot. Okay. The point is of this little script, okay, is that I'm trying to show you the relationship between the written form and the geometric form that we typically see. Like, there's a little bit of machinations that have to be gone through to get them to align. But essentially to find the all of this very easy. It's evaluating the same function either over all space or over specific things, and then the partial differential equation just means that I'm, evaluating the slope of this curve, basically. So that is there, and if I were to change this equation, it should work. Let's try something else. Okay. Okay. So this is A, so this is the scaling factor. Okay. So that is that's what that means. You're just intersecting with a plane and evaluating the derivative in a single space. We don't typically do that because we don't need to evaluate the derivative. We have other ways of finding that information. It's just that the partial derivative is a placeholder, is how we talk about those concepts when we speak about them in other contexts. So, like, it's a useful concept to have, even though you're not going to be evaluating it directly most of the time. Does that make sense to anyone? Okay. So these are like, I typically think of them as operators. Okay. So, like, addition or arithmetic operators, they act on numbers. The dot product and the cross product are vector operators. And then, there's also the translation, rotation, and scaling. And then there's Boolean operators. So you can think of all these things as just all these funny symbols as just ways of speaking about doing something. And so then there's this nabla symbol. This is not the same as the nabla dot. Nabla dot that we talked about earlier is the divergence. The divergence is like one of the vector calculus operation. The other one is what's called the gradient. Okay. And the gradient is just a way of packaging the partial derivatives into a vector. Why would anyone do that? Who the fuck knows? Actually, it's very useful, but like it doesn't mean anything. It's just a way of expressing the partial derivatives as a vector. Okay, that's what it means when you see that little nabla symbol in the Navier-Stokes equations. It means the partial derivatives as a vector. And really, what it means is often it means like those three equations that are packaged and represented as one. Okay. Now the gradient is like this. If I had this function and I wanted to take the partial derivatives, I would treat y as a constant, differentiate x cubed, which 3 comes down. This becomes 3x squared. The a, this should have been 1 over a. Excuse me, it's a mistake. This is a constant, so it drops away, and I get 3ax squared. To take the partial derivative with respect to x, I pretend x is a constant, differentiate the y cubed, and I get this, and then I package them as a vector. Now, it just so happens that the gradient also tells you the direction of steepest descent. It does. Miraculously, this is how you find the slope of anything in the world. If you know the function, and you don't need to know the function because we have computers. So we do the gradient, and the gradient tells you the direction of that you would have to walk up most steepestly. It just does. I can try to explain why. I will, but it's amazing. It does tell you that. So if I were to open up this if I open up this script here, there's another one here. If I open up implicit gradient, there's that thing that I just did, and here's the graph of the vector field, the same way I did before. So these are the partial derivatives that I just calculated manually, okay, just from the previous slide, evaluated down here at the same points. And you can see it is like a map of how you would have to walk on that surface, which is pretty cool. Okay, and you can also, by the way, you can also do that in Houdini. This is like there it is. That is this little thing, and then in here, I scattered a bunch of points on it, and then this is a little this calculates the gradient at every one of those points. And there it is, telling you this direction of walking on that weird surface. And that doesn't have a function. That is just a height field of a gooey surface. It needs to use a volume, just like the volumes we're using. It has some field of values, and of height. And the gradient function is a function that Houdini has, and it will tell you the slope of walking. So if I wanted to make an animation of water flowing down a hill, that's how I would do it. So that is and then by the way, if you do this, I want to show you this. This is cool. Okay. I projected them to the ground. Okay, I'm going to turn on this one. Oh crap. Why isn't it working? Did I screw this up? No, it better work. I'm so excited about this. Not working. Let's make sure this is, oh, it's not connected. Okay. No, I can use this one. Okay, this one's working. I don't know why the other one's not working right now. There's the gradient in plan. And here, okay, if I take the gradient and I do the cross product of the gradient with the normal vector, I get this situation where I have all these horizontally traveling perpendicular lines. That's because the normal vector is like that, and the gradient is like, pointing in the direction of walking up the slope. So if I do the cross product of the gradient and the normal vector, I get a horizontal line, contour. And then if I take the cross product again of the normal vector and the horizontal line, now I get the actual slope of the thing. Yes, indeed, I do. That is how it is done, folks. Take the cross product twice of the gradient, and that's the waterline. No math involved. It's just a field that is generated by the computer, and then it can interpolate values to find to calculate the gradient. Okay, so this in here, yes. No, the gradient is, yeah, the gradient is it's a vector. It takes a scalar function and returns just this vector. And it is not the slope. The gradient is the direction of steepest descent. And actually the magnitude is the slope. So it's like a 2D map of the function. It's a 2D vector. It's not a 3D vector. So like if I were to just show the gradient, if you do it in Houdini, actually it plots them at the height of the point. But it's a 2D, it's taking a function that's an X and Y function. Basically, like I have a height field. Like I have a height field. So it's just like what I did before. I have a plane with a bunch of points. And I'm evaluating each of those points at a function, at a height. Like that. And then I'm using that to build a surface. And then so I have a two-dimensional input space, and I'm just getting a single scalar value out of the two-dimensional input space. And I'm plotting that in 3 dimensions. It's ridiculous. I know. But like it's a 2D input space. I don't know how to, sometimes somebody's got to help me say these things better. It's a 2D input space with a 1D output. It's a scalar function. That is what a height field is, because it's all of these things. I could have easily mapped this as a 2D gradient, like a color field. But instead of the color would have been the Z value, the Z is the single output. Instead of mapping it as a color field, I mapped points which were where the Z value, the value of the function, is giving me the Z value at the surface. So it's a 2D input space with a 1D output mapped in 3-dimensional space.
of that, like arrow
Yeah.
is the slope.
That's right.
That makes
Yeah.
And how the like direction of steepest descent is.
Yeah.
It's probably, like,
Yeah. So, well, you wouldn't because I haven't talked about that at all. By the way, why it is that way is very complicated. It's not intuitive.
okay.
Why it is that way. I mean, it just so happens that it is. But why it is not intuitive. It's very confusing why it would be. You would have no way of knowing. It's completely opaque. It happens to be that it is, and I can try to explain why there are ways of understanding it, of course. But like the fact that it produces this is not is not obvious by any stretch of the imagination. But it is true that if you take the partial derivatives and you package them together, you get a map that is points in the direction that you would have to go to walk uphill. But it doesn't give you like a vector on the surface pointing in that way. It's like a 2D map of it. If I wanted the vectors on the surface, like I can take these vectors and do the cross product of the thing. Like I can do I have to turn them into 3D vectors like by some method. You know, I could do it in a different method. I could take the magnitude and move this point up by the magnitude and then unitize the vector. Like there are different ways that I could convert it into like a 3D vector. Right now, it's just a 2D representation of the surface. Yes.
Is it possible to create a gradient map of an object that like wraps into itself, so it's not just like
with the underside of it?
Yeah.
Yeah, I don't know. Like I don't think it's easy because yes is the answer, but it wouldn't have such a clear representation. Like these concepts are extendable like endlessly.
N dimension.
Yeah, you can do, but it wouldn't be clear. Like if you imagine like the gradient only operates on scalar functions, so it's very hard like to model a sphere because there's two values for every x. So like that is not really a 1D function. So like I can only really do half of it. I don't understand how I would do it the other way. I don't know if it can be done, if I'm being honest, like because as far as I understand it, it always is a 1D function output. But I'm fairly confident there are probably interpretations of it and ways of thinking of it not that way, but I don't know what they are. I only know how to think about it when the output is one number. You know, it's always confusing because it's always f of x, y, but this just means one number. Like it just means z or q or whatever you want to call it. It's just a notation. Okay, so it converts a 1D output to a 2D vector. So like that. So this is important. There's the one where I did the cross product on it to get the slope.
Half the sphere.
Correct. It's half the sphere because it's like I just made a height field. You can just make a height field in Houdini. So in Houdini, I just did like, look at this. I took a sphere. Here, and I said convert it into a height field. Oh, you can't see my stuff. Oh, this is doing the share only 1/2 of my universe. Okay, yeah, I took a sphere, converted it into a height field, scattered some points on it. Those points have the normals. And then in here, I said the normal, this is just the way it does it. It's confusing, just like, but basically it's just doing the gradient at every point using the height field. And the height field is just two values with a z. So it's a function. It's not really a function. It just is, doing it. It's doing it in a way I hope I have time to talk about. Like it's just sampling, right? Like just the same way we are dealing with fluids. Like basically it's got a grid of points and it's looking here, and looking there, and using those to imagine a slope. And then it's imagining a slope and using that to calculate the value. So it doesn't actually have a function, but the concept still survives. Okay. All right. So that is all right. This is my attempt, okay, to explain why I think this is going to be very confusing. Basically, like this is another way of thinking about a 1D function as mapping a 2D space onto a line. Like if you can imagine, like as I move around in this space, it moves around a point in a one-dimensional space. And these are the values over here that I have plotted above the points over here to imagine it as a surface, or that I've represented as colors to imagine it as a color map. And this, you can also imagine that if I were to, like, if I were to imagine this vector was very, very, very little, but still pointed in this direction, then I would have a tiny little partial derivative this way and a tiny little partial derivative this way. If I were to put those things, this little partial derivative and this little partial derivative, into a vector, it would tell me, like, basically you can see if I move this in some ways, sometimes it moves a lot and sometimes it moves a little. So like if it moves a lot, it means like when I move it a little bit over here, it means the partial derivative in the x component. If I move it this way and it moves a lot over here, it means the partial derivative is very big. If I move it this way and it barely moves at all, it means the partial derivative in x is very small. And vice versa, if I move it in y and it moves very much, it means the partial derivative is very big. And if I move it in y and moves very little, it means the partial derivative is very small. So packaging the x and y partial derivatives gives me a vector that tells me like the speed at which the function is changing, like in those local, right? Like it tells me like if I'm here and I move a little bit this way and a little bit this way, it's changing fast or slow. And this, by the way, I don't completely grasp this. It's just an intuition thing. Like, but if you imagine, like, if you imagine the vector that represents, I think this is going to be very confusing. Should I try? Yes, I'm started. If you imagine the vector that is, like, if you imagine a vector v in a plane like that, and then you imagine I have another vector that's like the partial derivatives packaged together, and I take the dot product of this little partial derivative vector and this vector in the space. If this vector was the partial derivative, it would be biggest. and any other direction that it points in, it's the product of the partial derivative and the vector would be littler. So like basically it means that if I combine these two vectors together, they're sort of telling me the steepest direction. I'm not getting at it very well. Maybe I'll try again. Basically, like it's just I don't know how to say it. Maybe it's because I don't completely get it myself that I can't say it. The idea is that as you move a point around in this space, the function changes to a varying degree. And it changes, there's an x component of that change and a y component of that change. You package those together, it sort of tells you the direction that is changing most quickly. That's sort of the idea. Okay, so all right. So divergence is also a concept from the same discussion. This is the same thing we talked about before. The idea, the formula for divergence is exactly what we did before. It's just the sum of the partial derivative. That's the mathematical formula. And that has to do, like, if you imagine a situation like this, remember the divergence is negative if stuff is flowing in, positive if stuff is flowing out, and zero if it's flowing through. If you imagine just getting rid of the y component of this at all, so you have only an x component. Like I should have had more arrows here. I'm imagining a river that is not changing in this direction, just flowing this way. So the divergence of any particular spot would be due only to the change in x. Then you can imagine, like in this situation, this arrow is pointing this way, there's no arrow here, and then there's an arrow pointing here. So the arrow is increasing in size. And this has positive divergence. This is another situation where the arrow is increasing in size as we look left to right. That's the rate of change, right? Is the derivative. So this has a positive rate of change, negative here, zero, positive. It's increasing in size as we move rightward. This has a positive rate of change, increasing in size as we move rightward. This has a negative rate of change. This one is bigger, zero, negative. So this one is decreasing as we move as a negative rate of change. And this one also has negative divergence, and this one has positive. So basically, the divergence is due to x alone is just greater. The greater is the partial derivative with respect to x. So, and the same logic goes for y. So you can just add the partial derivatives to get the divergence. Okay, then there's also the other one is curl. Curl is very funny. I'm not going to go into curl, by the way, because it's much more complicated to calculate, but it's very easy to imagine. Like if you imagine being on an inner tube in a river, flowing down the river, like sometimes you'll spin, like of your own, like the river will just rotate you. Even though you're moving this way, you're spinning locally. And that has to do with the fact that like maybe the river is flowing faster over here than it is over here. And so since I'm wide, there's like more force acting on me over here and I get spun. gets spun due to the changes like in the speed of the river around. So there's a rotation that's present in a velocity field just locally. Yes,
How is that related to the vorticity?
it's exactly related to it. So that in the vorticity confinement, that's what you do. You calculate the curl at any point, and then you pump it up.
So curl and vorticity are they like
I don't know why it's called vorticity. There's an algorithm called vorticity confinement, and what it means is like basically like I have a vector field like this, and I calculate the curl at this point, and then I increase the velocities, like the horizontal velocity and the vertical velocity. I increase them proportional to the curl to add vorticity. I think is a vague word. The curl is the rotation at a point. Vorticity is like just like a word that somebody used to describe that algorithm. I think.
okay?
Okay, so like
Application of curls.
the curl is the property of a vector field that is local rotation that is derived from the global motion. So there's the divergence is the property of a vector field that is stuff is flowing into a spot. The gradient is the property of a vector field that tells you the direction of maximum slope. The curl is the property of the vector field that tells you how much local rotation there is within it. And by the way, I want to skip ahead for a second. There's a very great video. I haven't watched this, by the way. It's very long, but I think my sense is it's very good. I watched like 5 minutes of it, and it was very clear. And so, like, I put it here because I think it explains these concepts in a longer, clearer format, probably than it might get bad, but the beginning of it was good. Okay. So I think it goes through the four vector operators: the divergence, gradient, curl, and the Laplacian, and they give you the different properties of a vector field. Okay. Curl is how much a vector field rotates locally, even though it's moving in one direction. Okay. So these are them. That's how they're written. The gradient is the vector. The divergence is the sum of the partial derivatives. The Laplacian, that thing, which I'll talk about in a second. And the curl is very confusing to calculate, but very easy to understand. Okay, so and you can see I wrote in the notes like some things about what they are. So that's there too. Like they are some okay. So by the way, the Laplacian is very cool, okay? Because the Laplacian is the gradient of the divergence. No, it's the divergence of the gradient. Okay, so the gradient gives you a vector of the steepest slope, and then the Laplacian takes the divergence of that and tells you basically what is a local maximum. Like the divergence tells you whether stuff is like flowing in or flowing out, right, to a spot, and the gradient tells you the steepest slope. So the divergence of the gradient tells you like whether stuff is flowing into a local spot on the direction of slopiness. So it tells you whether like a particular spot is like a very spiky. Like it tells you whether this spot is like much different than its surrounding. This is how viscosity is calculated, by the way. You look at how different any spot is from what's next to it locally. And then that's what describes how viscous it is, right? If it's moving if this particular spot is extremely different, it's scaled back. So you need the vector function that tells you how different something is. And this, by the way, this is in Houdini. Like, look at how hilarious this is. Like, this is, this one over here is just the, here it is. Volume analysis. You can just do it. Here, the Laplacian. gradient Laplacian. If I do the Laplacian on this height field, it returns that. Because that's the spot where shit's going crazy. This is the height field is most different from itself right there. Tells you moments of local extreme change. And I could map that as a color. Look at that. How cool is that shit? It's just telling me that a sphere intersecting a plane is like very fucking weird. Okay. And you can also do it on this. Okay, this is that smoky thing I showed you before. This smoky field. If I do the Laplacian on that, and then I represent it, like, look at it. It's telling me it's different. You can see it's different than it was over here. Let's me try that to make that clear. There's the fog. There's the fog. Very smooth fog. And then the Laplacian tells me where the speckles are in the fog. Tells me where is the moments of most difference out of the thing. So the curl tells me how fast I'm spinning. Laplacian tells me what's most extremely different only locally relative to what's right next to it. And the divergence tells me how much stuff is pouring in or pouring out. So these properties applied to a fluid allow us to describe different aspects of its relationship, with itself, to sort of understand different properties of it. They are ways of understanding the properties of a fluid, basically. Okay. So
is this similar to just a second order differentiation, like Laplacian?
Laplacian. So yeah, the Laplacian, like basically, yes, it's a second order. The gradient returns the gradient returns a vector. The divergence takes a vector field and returns a scalar. The gradient tells you how much something is sloping. So I look at a scalar field, I take the gradient, tells me how much something is sloping. Then I take the divergence of that tells me how much the slope is pouring into a spot or pushing out from a spot. So it's a second order derivative. First I found out where was the direction of steepest descent, and then I find out how much the direction of steepest descent is pouring into a spot or pushing out from the spot. That tells me how much any particular spot is a local point or is a local maximum or minimum. Why is this relevant? I have to say, like, I only find it relevant because I think when I was a student, I remember, like, I had lectures on computation. I didn't understand a word of them. And then I remember, like, later on when I was reading things, like, I was like, oh yeah, I feel like I've heard that before. And then I like went back and I feel like over time, I feel like I can walk into rooms and understand things that people are saying to me because I've heard the words over and over and over again. And so I feel like you guys are young. I feel like if you see the way people talk about things in this sort of a field, you'll then be able to, listen to things like that without feeling like it's something weird and strange. So I don't know. This is the language of fluids, and that's how it is. Okay, so now when you look at this momentum equation, what it says is it's just a bunch of these vector operations. It's the partial differential of the speed with respect to time. Then it's the velocity times the gradient of the velocity field, yada, yada, yada. By the way, I don't worry about that. We'll get to that in a second. It's not necessary to parse it in that way. I'm only saying that these those functions represent other things. So if you were to expand this, it looks like that. That's what it actually means. Okay. It's just a bunch of partial differential symbols. So like it's actually three equations, one for U, one for V, one for W. This is the term for viscosity. It's a multiplier times the Laplacian. So it's telling me I multiply the viscosity times how much any particular spot is very different to sort of smush everything back into being the same. And then this is the other ones as well. We can get into that in a second. But like the ones that I worry about are that one, the divergence, and the Laplacian makes sense to me there. Okay. We talked about that. We talked about incompressibility. We talked about this before. Okay. So then, how am I doing? Running out of time. I'm out of time. I am going to skip some of this. Okay. So just to sort of get to the end, which is like basically, the Navier-Stokes equation is really Newton's second law rephrased. So it's this. It says the mass times the acceleration equals the force. And then the acceleration is the speed, the differentiation of the speed with respect to time. And then the force is gravity plus pressure plus viscosity. And then the terms are written in the terms of related to the speed that we just discussed. So the pressure is, they're given in terms of the properties of a vector field. There's mg, there's the gradient of the pressure field, there's the viscosity one that I talked about, divided by v, and you get this, which is this usual form of the Navier-Stokes equation. And then there's something very tricky that happens to convert this term, which is from the Lagrangian point of view. This is like any particular particle, the acceleration of that particle, which is the speed with respect to time, is equal to all the forces. To convert that to the Eulerian point of view is a little interesting, I think, but complicated, and it involves like some stuff like this, which I'll talk about, maybe not, but you can rewrite it like from the Eulerian point of view, and it's slightly different. Okay, and that's what leads to this equation. And then in order to write a fluid simulator, usually we start by dropping viscosity, and then we split it apart. So that's the Euler equation, and then we do the advection, which says this differentiate the speed. The differentiation of the speed is equal to the velocity times the gradient of the velocity. Then we do add the forces. Then we do the pressure projection. So basically, we take each of the terms of the Navier-Stokes equation, and we separate them out one by one to evaluate them that way. Okay, and then there's adding heat, blah, 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 blah. Okay, this is what I wanted to end with. So this is what's called the finite element method. Okay, this is how these things apply to grids. We don't think about functions anymore. We never think about calculus again. We think about this is how there are three ways that this is done in computationally. They're called the finite element method, the finite volume method, and the finite difference method. The finite element method is this one. Basically, the partial derivative with respect to x is just the value of this cell minus the value of this cell. That would give you the partial differential with respect to y there. and the value of the partial differential with respect to x is the value of this cell minus the value of that cell, divided by the step size. So that is the formal definition. It's just like a normal limit expression for a differential for the derivative. It's plus a little step minus another position divided by the step size. So that's how it's doing it in Houdini. You just go forward by the step size, forward by the step size, subtract, and divide by the step size. And when the step size is little, it approaches the correct value. So this is all of those functions have discrete versions which exist on a grid like this and don't require having any function at all. And that is how computers evaluate these functions. You could calculate there's a discrete version of the gradient, and it's just that as a vector. There's a discrete version of the divergence, and it's just that plus that. And so you just look at the values that you have in your system and you evaluate them. And on a staggered grid, it's a little more complicated. Okay, I've already talked about this. And then there's the finite volume method. Okay, and this is what's usually done. So we are using we're using a kind of a hybrid, but the finite volume method is a little different. You don't use you have little pockets of space, and you look at the flow going in and the flow going out to that little pocket of space. And basically, it's a little trickier because they always say they're integrating over the volume of the little cell. And all that means is like they're no longer thinking about the value at a point, but they're thinking about how much stuff is actually in the volume. That's the difference. So you have to use a slightly different version of the equations. All the equations that I was showing you, they have all the partial symbols in them, which means they're looking at tiny little points. And in order to do the finite volume method, you have to integrate the partial differential equations to figure out how much volume is in the thing. But that is what is done in like ANSYS or something, where you have like a mesh like this that has an unstructured cell. You use the finite volume method instead, and you're thinking about how much stuff is in this little volume rather than the point in space. So there's like structured meshes and unstructured meshes like this and like that. Let me skip all this for now. We can look at that stuff later. Just wanted to say that these are the two versions. The finite difference method is not really done very often. The ones that are done more typically is this: the finite element method. The finite difference method is the one that is done. The finite element method is not done that often, except in like structural stress. The finite difference method is for volumes with points dealing with infinitesimal quantities in space. The finite volume method takes all of the quantities in here, sums them up, and so you have to integrate the partial differential equations in order to calculate what your new equation is, and then you can deal with the flow going out of the surfaces. And that is what is done when you have an unstructured grid like this. The point of the unstructured grid is it allows you to evaluate the laminar layer more accurately than you evaluate the other layers, like all the way out in space. So that is typically what is done in that case. Okay, so I will hang out and talk to anybody who wants to about their project or go through the Navier-Stokes equations if you want. But my main purpose in going through this stuff with you is only one. It's basically wasted 3 hours of your life for one purpose, which is that like I really don't know what incredible things you guys are going to do in your lives. And I think you should know that you have the capacity to have maximum fluency in any language, mathematics, computation, architectural, any language that you want. You are so early in your careers, and all of this stuff is so within your capacity that I feel like you need to know that now, so that you know that you should imagine that you can do anything in the world, and not that there's a particular subject that is, too esoteric to go into. Okay? All right. I'm done.
Okay.